Hi, Sriharitha. This is Professor Ravi Shankar.
Hello?
Yeah. We can able to hear you. So we will start at 7:30. Okay.
Yes.
Thank you. So we will wait for some time, and once all the people join, then we'll start at 7:30. So the talk will take 1.5 hours. You can plan actually. Thank you.
I'll share my screen meanwhile.
If you want to share and check, you can share and check.
Okay. I'll do it. Okay. So basically in today's talk, I'll be giving a glimpse of some of the tribological properties of alumina matrix composites. So alumina is a biomaterial, right? So therefore, first of all, I will show you how we have prepared this alumina matrix composites and also testing of this by using some of the 4-point bending experiments, as well as finally we will show you about the tribological properties. So let me go ahead. So the contents will be just 1 or 2 slides on my academic journey and what here in FML, the Functional Materials Laboratory, we have. And then I'm going to directly go to the talk. Okay. So essentially, if you look at this diagram, we are going to understand the tribological properties of self-mating alumina system, and wherein it's not a fully dense system, but rather it has got some mesopores. So to begin with, yes, my academic journey, I did my integrated BTech and MTech at IIT Madras in the metallurgical and materials engineering. In that, I had worked with high entropy alloys, synthesis and characterizations of it. Later on, I moved to EPFL in Switzerland to do my PhD and jointly at EMPA. So over there, I have got experience in wetting, tribology, as well as soft lithography techniques. Primarily on ceramics and also to a very good extent also on polymers. So after completing the PhD, I stayed in the same lab at EMPA for 5 more months to work on solar related applications. Then I moved to Paul-Scherrer Institute in Switzerland. Again, it's in the Zurich part of Switzerland. So there I was working in the nuclear laboratory. We were trying to understand what happens if we add platinum nano catalyst particles and if it can reduce the oxygen present in the environment. By that, you can actually reduce the stress corrosion cracking issues that the nuclear power plants are having in the Switzerland. So it was a very, very applied project that I had worked in my postdoctoral research. So after I completed in 2019, I moved to IIT Gandhinagar into December 2019 as an assistant professor. And I'm actually the group leader of this functional materials laboratory. So at FML, what do we do? So these are the 3 or 4 verticals that you can see. Firstly, we are very much interested in the processing of materials. So the processings involve 2 methodologies. One is that we are basically looking at metallurgical routes like cold compaction, sintering, and spark plasma sintering, etc. And then second methodology is the wet chemistry routes like slip casting, tape casting, spin coating, and things like that. So by using those 2 methodologies, we wanted to produce porous materials. We also, of course, wanted to produce bulk specimens as a reference, but we are rather more interested in the porous materials. And we also look at soft lithography techniques like colloidal lithography, replica molding, hot embossing, etc., so that we can create some sort of regular roughness features on the surface. So these are, for example, pillars, conical pillars, which are having micron dimensions. And then you also have this sort of channels. You can also not just these regular things, but in principle, you can make a very irregular free form also. So you can also put your IIT Tirupati or IIT Gandhinagar, micro emblems on your materials. So it's all possible. So after we prepare these materials, these textured or patterned materials as well as porous materials, we typically test them to understand what happens in terms of the wetting. That means on these surfaces, we are going to do some surface treatment and investigate with water. Here you see some paints, and then we also currently are investigating with bacteria, right? And then many more real life fluids. In one of the project, which is almost completed, we have tested 30 real life fluids and have shown that all of those liquids can be repellent on the material that we have prepared. So that is actually going to lead to a very nice industrial application. Then finally, we're also interested in investigating tribological properties of the materials that we have processed and developed. So tribology, we work with all sort of configurations, in the sense pin on disc for the scratch testing. We also look at spear on disc. Then we also look at flat on flat configurations. And right now we are almost, the procurement is going to be done, finishing in 2 months. So we are going to have a tribo corrosion unit also, and that can also go until 500 degrees Celsius. So these are the typical things we do here at FML. So then let's move on. And then currently I have around 9 to 10 group members or students. And I would like also to advertise that there are some PhD and MTech positions. So if you are interested in the kind of work that we are doing, do write to me, or also you can look at the IIT Gandhinagar website and apply through the regular opportunities you can have. So let us then start the scientific part. So coming to the introduction of tribology, for those people who are not very much aware, so tribology is essentially coming from the Greek word tribos, which means rubbing of materials, and ology means study of these materials which are actually having physical contact and they're sliding against each other. Okay, so it deals with three things. One is friction, another one is wear, and the third one is lubrication. So right now what you have seen is that the blue material is called as the counter body, and the bottom one is called simply your bottom specimen. So when there is a sliding here, you actually see something like a simple pendulum. So the velocity is neither constant in magnitude or direction between these two sliding materials. But if you are looking at rotary kind of a module, then you can basically have a sphere rotating on the disc. In this case, your magnitude at least is certainly constant. So depending on what application we are targeting, we can basically choose what is the type of test we wanted to conduct. Now, as you know, friction is essentially the resistance to motion of one body moving against another, right? And therefore we have static friction coefficient, kinetic friction coefficient to basically characterize the material surface. Then we have the wear. It is essentially the loss of material due to this relative motion, and the material that was removed from these two sliding surfaces is called as the wear debris. So the wear debris can be micron sized, even nano sized, or even macro size also is possible. So lubrication, it need not always be just liquids. It could also be solid lubricants, like for example, molybdenum disulfide, graphene, waxes, and so on. So in one of the project, DST project, in fact, we are working with solid lubricants, which is like Teflon. So that's for seismic isolation. So, yeah, depending on the temperatures, depending on applications, one could actually choose your particular lubricant. So right now the theme is actually biomedical applications. So therefore I'm focusing typically on alumina system. And the very last 1 or 2 slide, I'll be also talking about zirconium oxide, because this is also a dental implant material. So actually, if you know, in the hip implant, it's possible to have, metal on polymer, or metal on metal, or you can also have ceramic on ceramic, and they are not in static, but essentially there is a rubbing, and therefore tribology of these materials are actually important. Not just tribology, definitely fouling is important. Also, what happens to these weight debris as they get ejected into the body. So it's, real life problems are always multidisciplinary in nature. And right now we are only primarily focusing on the tribology. Okay, so the strategy here is that we are going to prepare a porous aluminum oxide and impregnate the pores with this liquid. This blue liquid is actually its liquid. So it's a very high viscosity liquid we would like to impregnate it with. And then we are going to study what happens if I am having a counter body sliding against this composite surface. So taking aluminum oxide, it is definitely a very hard material. On Mohs scale, at least on the old Mohs scale, it is 9, right? So having this mesoporosity, mesopores means the pore sizes between 2 and 50 nanometers is called as a mesoporous material. So mesopores will actually help in having a very high capillary forces for your lubricant, and thereby whenever the liquid is taken off from the surface during this sliding, these pores will help to replenish the liquid from the material. That's the reason why do we have the mesopores and not the bigger pores. Then these, as you also know, on the surface, these act also like sort of a reservoirs. So let's go and see what can we do with this system. So yes, the first thing is that we have to first of all prepare these materials, and for that what can be done is we have purchased aluminum oxide nanopowders, but however, because of the very high surface energy they have, they actually end up being agglomerated. This is an SEM picture of as received material, and if you will actually zoom into one of the agglomerate, you are actually able to see nanograins. So if you can quantify that, the grain sizes are in the range of 150 nanometers or so, and in principle we have also characterized the particle sizes after de-agglomerating these powders, and here we can see that DB50 is 150 nanometer, DB90 is 220, and DB99 is 330. So what this means is that DB50 means 50% of the particles have size 150 nanometer. So similarly, 90% of the particles have size less than or equal to 220 nanometer. In that way, you can basically interpret it. So what we can say is that, of course, it's a distribution. It's never single value when you are looking at particle sizes. So you can actually say that predominantly the sizes are around or less than 200 nanometers or so. So these powders, now these as received powders, we can add a binder. It's called polyacrylic acid. So it's 2% polyacrylic acid, and rest of it is essentially water. So we can adjust the pH by adding ammonium hydroxide, and then if you stir it for 30 minutes or so using a magnetic stirrer, then you are still going to have the agglomerated alumina slurry. Then you will add some little bit of octanol so that the interfacial tension between the liquid and the air can be minimized, thereby helping to break down any air bubbles that are present in between these agglomerates. Okay, if you don't do that, and if you will cast it ultimately, then you are going to end up having very big unintentional or undesirable sort of voids in your material. We don't want that. So you have to break down all the air bumps present in the material, in the slurry. So this agglomerated slurry is not good to cast. So you have to further do a de-agglomeration process. For that, we have employed 3 steps. The first thing is that you have to do a probe sonication, using this probe sonicator. So for around 20 minutes or so. Later on, we are going to use this low energy milling. You can put this slurry and roll it for almost 2 days or 3 days. And finally, you can do a degassing so that any air bubbles that are present will be removed from the slurry. So finally, you are able to achieve almost a de-agglomerated slurry. Here, each grain is a particle. Now, you can take this nicely de-agglomerated slurry and essentially cast it. So, but then, then there will be a question. So how much should I add? What is the solid fraction of the aluminum oxide in this slurry? Should I make it very much like a paste? Should I make it more like a more flowing sort of a slurry? What is the solid fraction that is best? So for that, we have to essentially look at the viscosity of these slurries. So you can use we have used rotary type of a viscometer, and we have obtained shear stress and shear strain rates. So that particular data is this black data, right? These data points. So in principle, we know that it has got a yield stress because it is not, that it is a linear graph, of course. So, but then it is not passing through origin. So that means my slurry is essentially following a Bingham plastic behavior. It is not directly a Newtonian fluid. Water is a Newtonian fluid, but here the slurry is not. So you can use this expression and try to find out what is the viscosity. So essentially, look at this particular blue one. It's actually the viscosity that is plotted. So now we can change the alumina solid fraction from a small value until relatively some 37-40 volume fraction or so, and see that viscosity is consistently increasing as you are increasing the solid fraction, which is pretty much obvious. Now what I have done is I have taken this is actually my PhD work, so that's why I'm referring it as I. So what I have done is that this particular samples with different viscosities I have casted into molds, let them dry, also sintered them and looked at them in SEM. So once I did that, I was able to see that this particular sample was not completely de-agglomerated because quite a lot of if you look at the this particular incomplete de-agglomerated slurry, so quite a lot of big micro holes are present on the sample. However, if I'm able to see this particular sample after casting, after drying and sintering, then the SEM or any confocal microscope image looks like this, which means there are no such micro holes. So we will continue to use 25 volume percentage as the optimum solid fraction for the rest of the experiments. Now, this particular slurry is nicely de-agglomerated and we are going to cast it into some mold. So for that, we have to do some assembly. What we have to do is, firstly, we will prepare this base, this yellow colored base that you see. It's actually plaster of Paris. Plaster of Paris is nothing but calcium sulfate dot 0.5 water. Now on the top of it, we are going to place a filter paper, and on the top of it, we are going to place a some sort of a silicone mold. So if you don't know what silicone is, your phone covers you are using, right? That is essentially silicone mold, silicone material. So it's relatively elastic in nature, and this particular mold is open from the bottom as well as from the top. So that now in these cuboids and also these particular cavities, we can pour alumina slurry, whatever we have prepared, and let it dry. So the drying happens in two stages. Firstly, you have to dry it at 90% relative humidity for 24 hours, and later on at 45% relative humidity for 2 more days. This will allow for very slow drying. Otherwise, you are going, if you dry it very quickly, then the samples will end up breaking. There will be cracks that will generate in the sample. So after nicely drying it, whatever you are able to demold from this silicone cavities, they look like this. So this is what is our self-mating pair for our tribological test. So the bottom specimen looks like more like a cuboid, and the top specimen looks more like a cylinder, and we are going to end up having a flat on flat configuration. So these green compacts, definitely, if you remember, there was polyacrylic acid, there was octanol, and ammonium hydroxide, things like that. At least we have to get rid of all the organic materials present in the sample. So therefore, first of all, we'll do a pre-sintering step at 600 degrees Celsius. We'll heat from room temperature to 600 degrees Celsius very slowly. That is 1 degree Celsius per minute. And at 600, we are actually going to hold it for 1 more hour and let it cool in the furnace. So the pre-sintered compacts are obtained after we remove all the organic binders. Now from the pre-sintered compacts, we are going to do a conventional sintering in air because it's an oxide, so it's okay to do it in air. So sintering is done at different temperatures so that we are going to control the porosity of the specimen. If you look at the, is there any question from the audience? Can I go ahead?
Yes, madam, you are.
Okay, okay, great, thank you. So what after sintering, so sintering was done at some temperatures based on the melting point. So we know that aluminum oxide has got a melting point of 2072 degrees Celsius, and usually when we want to pick up our sintering temperatures, we would tend to pick up more than 0.4 times the melting point, wherein that should be in the Kelvin scale. So we then I had optimized and said that for different temperatures, I am able to get different densities. So at 1150 degrees Celsius, the sample is having around 70% density. That means 30% is porosity. And 1205, it's 80%. 1250, it's 90%. And until 1250 degrees Celsius, you see more or less the grains are having similar size. So that means there is not much grain growth. However, at 1325 degrees Celsius, first of all, you already started seeing that the grains are coming quite near to each other. So that is, grain boundaries area is increasing dramatically, as well as the grains have also started becoming slightly bigger. So grain growth also has started. And then if you center at 1400 or 1500, you actually see a very elongated grains in those materials. So these 5 samples were taken for further experiments. So one could actually do grain size analysis, get the average diameters, and this particular graph on the right hand side, you can actually say that it's a your green body or a pre-sintered body is going to have around 150 nanometer, and for 70, 80, 90, the grain size are not changing significantly, while for 95, it has increased to almost 330 nanometers or so. And however, for the 99.5% density, which was this particular case here, the grain sizes are almost around 1 to 2 microns. So it is no longer in the nano size, but it is almost like a micro-sized grains. Now, so if you look at this sintering plot, that is, if you plot the relative densities as a function of sintering temperature, as I just said, that below a particular temperature, your ultra-fine grains are rated, but beyond that particular sintering temperature, there is a grain growth that is happening. So now we needed to quantify the density and porosity. It is porosity here. It is not simply just one value. Here we have to understand that the material can have open porosity as well as closed porosity. Thereby, we will use Archimedes principle, but in a slightly different manner. So what we can do is, we are going to bury the samples in the air, that is your so-called dry weight, and you can submerge your sample in the liquid. Let all the liquid penetrate into the open porosity of the sample. That's called as immersed weight. And then after it is saturated, after all the liquid has been into the pores, you can take it out, wipe all the lateral surfaces with a lint-free tissue paper, and then again weight, that is so called as wet weight. Using these 3 weights, one could actually measure the open porosity fraction in the material, as well as the relative density of the material. Once we know these 2 values, your total porosity is nothing but 100 minus your relative density. If I know total porosity and if I know open porosity, then your closed porosity is nothing but total porosity minus open porosity. Okay. So using this particular expressions, I have quantified what is the open, closed, total, porosity and relative density for all the specimens. And this is the trend. Essentially, what is happening is that in the 70, 80 and 90, definitely when the total porosity is decreasing, your open porosity will also decrease, which is okay. What you have to remember here is, if you look at the closed porosity values, it is not changing much. Okay. So it means that until 90% density or so, most of the porosity is actually open. But however, for the 95%, you see that closed porosity is much more compared to the open porosity in that material. And definitely for the 99.5, then you don't have any porosity. Okay, or let's say not very significant amount of porosity is present. So that's the porosity information. Then we also wanted to characterize the pore sizes, right? For that we have taken mercury intrusion porosimetry method, and this is the so-called your Lucas-Washburn equation, which says that if I see your mercury, it's a metal, okay, and it has got a surface tension of around 480 millinewton per meter. Why am I talking about surface tension? So if you have a very, very high surface tension of a liquid, then it prefers to be in a spherical shape. It doesn't like to wet on the solid. Now in the mercury intrusion porosimetry, what is happening is that the mercury has to be pushed through the pores of alumina. If you simply put mercury on the porous alumina, it is not going to go enter into the pore because of its very, very high surface tension. It would prefer to be simply like a spherical drop. But the same aluminum oxide, porous aluminum oxide, you take and place one drop of water on it, water will immediately go inside. Okay, but mercury is not going to go inside. So because it is not going to go inside, you have to apply a pressure, which is here P, it's called intrusion pressure. And gamma here is actually, it's gamma, not gamma 1, it's gamma of mercury. Okay, it's a surface tension of mercury. As I said, it's 480 millinewton per meter, and theta is the contact angle of mercury with aluminum oxide, and that comes out to be 140 degrees. And R here, which is my pore radius, that is something I wanted to estimate for my samples, or basically measure for my samples. So I'm going to use this particular experiment, and we were able to get this pore size diameters for the samples. For the 95, because it's a lot, it's quite close porosity, we were not able to get any pore size distribution values. And but do remember, guys, that this equation is actually developed for cylindrical pores, but in our case we don't have cylindrical pores. It's quite like a network. So that means this equation is not, this whatever values that you're actually measuring are not the precise values that the sample has. All right. But then there are no but better models to be able to bring from your measurements to your porosity values. So we had to use this approximation. Certainly, if somebody tries to develop a better model for this sort of random network porous blocks, it is a very good scientific contribution. All right. So then for these specimens, because we started off with alpha Al2O3, but then if we are centering at higher temperatures, would it convert to gamma Al2O3, or would it convert to some other phase? That needs to be confirmed. And for that, we have done some XRD analysis and found out that the phases are not changing. But then we use this to find out the crystallite sizes and compared with the grain sizes. So that using this Scherer analysis. Okay, these sintered samples, whatever we have got, we cannot directly use it for our tribological testing, because the surfaces are going to be having a lot of, flatness issues. There will be a lot of waviness, and then there will be also quite a lot of roughness, because your grains are not fully sintered. So it is definitely essential to polish the specimens. So for that, silicon emery sheets, silicon carbide emery sheets were used, and followed by alumina slurries. Okay, almost up to 0.1 micron, or actually it's wrong, it's 0.01 micron. I have let me correct it. It is 0.01 micron alumina particles were there in the slurries, and all the way from very, very coarse silicon carbide emery sheet, I have polished until using alumina slurries. Final samples after polishing, they look like this. For the 70, 80 and 90%, you see that there is a region called debris compacted region. Okay, that is essentially because your polishing is also like like an abrasive, the mechanism actually is abrasive wear. So it's happened here in these regions. This is all tribosintered regions, and we can call it as debris compacted region. And still some regions are porous regions. However, for 95 and 99%, 99.5% in samples, predominantly the samples are having quite a lot of smooth surfaces. This is not very much representative. I am just trying to show that for the 95% dense, there are a few places where there are some small amount of porosities, and this is actually could be your closed pore, but due to the polishing, that closed pore would have opened up on the surface. Okay, and this is the Kikuchi pattern I am trying to show for the sapphire, which is a single crystal, because that was used as a reference when we have done the tribological testing of these 5 materials. Okay, so after polishing, if you look at the roughness, then you can see that different roughness parameters are plotted: RA, RP, RQ, RZ, etc. And you see that with increase in density of the samples, your roughness has decreased, which is obvious because when you have higher density, your grains, which are like spherical balls or so, the the what do you call, the contact between them is very minimum. So if this is the contact, definitely there is this sort of roughness. But if the contact is very high, and then the atoms are diffusing during the sintering process, it actually tends to remove the curvatures in the sintering process and sort of makes it more flatter. That is why your roughness is decreasing with increase in the density. Okay, and if you will simply just zoom in this RA value, this is actually the trend, although it sort of seems more flat, but because it's very high values are given here on the y-axis, so the average roughness RA value is again decreasing with increase in the density. We have also confirmed that with the AFM measurements and saw the similar trend. Exact values we don't get it, because definitely in the AFM we have used a tapping mode, while here in this case we have used a contact. Okay. Well, then the surface porosity. We know the bulk porosity fraction, but what about surface porosity? For 70%, 80%, 90% dense samples, we can take several of these SEM pictures and basically say that I'm going to look at how much is this debris compacted regions. I have done that analysis, and we can say that 70 to 75% of the surface is actually this debris compacted region. So only around 30% or so is actually this porous region. In that 30%, remember that in the 70% density, that means 30% of 30% is the surface porosity. For the 80% density samples, it is 20% of the 30%. Isn't it, guys? And for the 90%, 10% of the 30%. So the surface porosity is obviously different for different specimens, but more or less we can say the debris compacted regions have similar area fractions for 70, 80 and 90% samples. Now that we have nicely prepared the specimens, first of all we needed to do some bending experiments, because if we want to work with porous specimens, then the first question will be, did you first of all investigate the mechanical properties? Is the strength good enough to be able to use as a porous material, right? So that's why we have tested the flexure strength using the 4-point bending experiments, and this is the typical setup. It's actually as per the STM standard. So the flexure strength is given by this formula 3 times. The F is the load that is applied. Is in this diagram, it's actually given as P, either F or P here. And D is the roller length. Okay. And then B is the width of the specimen. If this is your width, then T thickness will be into the plane of the screen, thickness of the specimen. So these values are as per the STM standards. So again, we will use slip casting method, because these specimen dimensions are different as compared to the samples that we need for tribology. Once we get these long specimens, we can put the specimen here and we can apply a load here. And then you see that this is 1, this is 2, 3, and 4. There are 4 points. That's why it's 4-point bending. So we can simply break it and find out what is the flexure strength for this particular sample. So we have done it for I mean, again, these are characterizations, because do remember that once you have different dimensions, and if you place them in the same furnace, then again your microstructural properties can be different. So one has to know all the properties like pore fraction, density, grain sizes, etc. for different centering temperatures. So that's okay. Then we will look at the flexure strength data. So totally, I have made 50 specimens for each, 50 specimens in total. So look at this. This particular batch of samples is for 1300 degrees Celsius sintered samples. Another one is 1350, 1400, and then it's 1500. So if you will plot it as a function of sintering temperature, you don't see any trend. However, if you plot the flexure strength as a function of total porosity fraction, there seems to be some trend. That means your flexure strength is decreasing with increase in porosity. That sort of makes sense. Then what if you plot as a function of open porosity fraction? Then this is the sort of diagram you get it. But do remember, guys, in your samples, it is not only the porosity that is changing, but the grain sizes are also changing, and they are not changing in a particular trend. So it is important to deconvolute this effect of porosity and the grain sizes. So for example, look at this particular diagram. If I will try to see what is the grain size of this one, then this is actually this point here. And if I will say what is the grain size of this one, so this is this point here. So you can take selected points in this particular diagram and try to plot, trying to understand if at all maybe there is a special trend where the flexure strength is depending on the grain size. It seems to have some sort of a trend like this, but again, this is an outlier. So it is very difficult to interpret in that way. As long as only one parameter doesn't change, it's a little bit difficult. However, what we can take as a key message is that the flexure strength values of these porous materials are as high as 550, but they can be as small as around 250 megapascal. With that key message, let us see what is the literature values of alumina samples look like. If we look at that, then actually you see that these are all the literature data that I have picked up from several sources, and I have plotted them. So firstly, the flexure strength as a function of grain diameter is plotted, and you actually see that this is a very nice sort of a trend that follows. And these things like CIP, HP, they means like HP is for hot pressing, CP is, for example, cold pressing, SC is slip casting. These are all the processing methodologies. Okay, S is for sintering and so on. And when you pick up the not much literature, first of all, is available for flexure strength measurements as a function of porosity. There are a few articles, and if you plot that, then you can see that on y-axis, the flexure strength values are around 225 or so, and as the porosity fraction has actually increased, obviously the flexure strength has dropped. So I want to tell that comparing with the data we got and with the literature, we can say that alumina samples showcased better or similar flexure strength as compared to literature. So it's okay to continue with these substrates and conduct our tribological testing. So before we wanted to do a tribological testing, we are not going to simply do a solid and a solid, but rather we said we are going to impregnate the pores with a high viscosity liquid. Okay, if it is a high viscosity liquid, then typically impregnating at room temperature is going to be a problem. So whatever conditions in this slide you see is for the so-called formalin oil. Formalin oil is like a perfluoropolyether. Typically, people use it in sort of vacuum pumps for very, very long period of time. It can be used without having significant evaporation. So at 20 degrees Celsius, if you will try to this is your specimen, it's your porous aluminum block, and if you dip it in something like this oil, which is a high viscosity oil at room temperature, and if you leave it for 2 hours, obviously because this oil likes aluminum oxide, it will, through capillary action, the oil will go through the pores, but only 40% of it was filled. this I got by simply weighing the sample before and after and comparing it with the open porosity volume that the sample had. Okay, so only 40% was filled. Then I said, okay, let me take it to a higher temperature of 150 degrees Celsius. And for 1 hour, then 96% was filled. If you do it for 2 hours of impregnation, almost 99.5% was filled. So remember that we cannot go much more beyond than 200 degrees or so, because the oil will start degrading further. So we can say that my optimal impregnation conditions are around 150 degrees Celsius and 2 hours. After we have now impregnated the oil into the pores, we can go ahead and test the tribological properties. For that, we are going to use predominantly flat and flat configuration. So flat and flat configuration means the interface between the counter body, which is here a cylinder, and the bottom sample, which is a cuboid, that interface is going to be an area contact. Okay, that's why it's a flat on flat configuration. Now, when in this case, there are different counter bodies. Mostly we are going with a diamond counter body, but in sometimes, sorry, excuse me. Mostly I went with dry alumina samples. In very couple of tests only, I went with diamond counter body. Okay, so then here the bottom is impregnated while the top is not impregnated. That's why we call it as dry specimen. Then the loading is between 10 to 220 Newton. That is the full range of the tribometer. It's an SRB tribometer that I have used in Switzerland, and that means the pressure is around up to 10 megapascals also. And this is the real digital image, how the the holders look like. And this particular holder was specially designed so that usually in the flat on flat configuration, when you try to bring them together, there can be sometimes, actually most of the times, there will be an alignment issue. If you do not correct it, it is possible that at one part there will be a huge pressure. That means locally the crack can initiate and the samples can fracture very badly. So you have to really make sure the surfaces are as flat as possible, or let's say as aligned as possible with the other material. So for that, this particular holder is able to have a slight rotation in this manner, as well as it can move a little bit in this manner. This will help to self-align. This will help to better self-align the interfaces. So that is the sort of testing. Now we can change several things and study the tribological properties. First thing obviously is we are changing the density of our substrate, which is alumina. Second thing is I have tested with different lubricants also. Today I'm not going to show about all the liquids. I'm primarily concentrating on the best lubricant, which is the formalin oil. But one can actually in principle change the lubricants. Then for the case of formalin oil, we can change the viscosity of it by simply heating it to higher temperature. And we can change the sliding speed. That means we are changing the sliding distance. We can also change the applied normal load also. Okay, so here, if you have your substrate to be a porous material, then it is called as lubricant infused or impregnated situation, because it's actually getting infused. If it is a fully dense specimen, like 95 or 99.5%. Why did I say 95 as a fully dense? Because it has got predominantly closed porosity, but not open porosity. And obviously the liquid cannot enter into your closed porosity. Okay, so that means both these two densities actually fall into this sort of configuration, wherein the oil is mostly lying on the surface of the sample. So it is a lubricated situation. That everybody sort of knows. While in these three materials, 70, 80, 90%, it is an infused situation. Okay, so we are going to now see whether this is going to perform by any chance better than the lubricated, or our conventional lubricated systems are only better. Let's see what happens. Yes, so yeah, before this particular conclusion, I already said that among the three liquids, formalin oil was the best lubricant, I said. So actually, there are some reasons I wanted to show you why it is. So if you look at the density of all the lubricants, there are like, 5 liquids initially I began with. Formalin oil has higher density. Then if you look at viscosity, it has higher viscosity, and evaporation rate is smaller. So you want the viscosity of your oil to be higher, right? Then only the solid contacts between your counter body and the bottom specimen are going to be minimized. Remember your Strieback curve. It's better to have high viscosity oil. Then evaporation rate. You don't want the liquid to be evaporating quickly. Then you also want the capillary time of the oil to be actually smaller. But in this case, it's a trade-off. Formalin oil is not doing very well. We want the least capillary time so that the oil can replenish very quickly. Then we also have to see the dimensions. So water, hexadecane, formalin oil. If you look at the dimensions, formalin oil is having a much bigger molecule. Actually, these are much bigger molecules. The higher the molecular sizes, again, the separation between the solid contacts is going to increase, and hence we are going to have lower friction coefficients. So in that way, again, formalin oil is good. So then looking at surface diffusivity. What if I have now, after several cycles, some of the oil has been rubbed away from the main contact area? Then the oil should be able to come back to that area between these two solids. For that, it's actually surface diffusion process. It's like molecular walking. Okay, so surface diffusion process has to be very high. But then unfortunately, because it has got a higher viscosity, here it is sort of like a trade-off. Surface diffusion process is not very good for the formalin oil. And then you also want that particular oil to be bonded to my substrate very, very nicely. Okay, so that's what we tend to characterize it with so-called interfacial van der Waals forces of attraction with alumina. And most of the liquids, except water, are reasonable in the same range. Water definitely is a specialty because it can form hydrogen bonding with aluminum oxide. Anyways, but the rest of the properties of water are not the best. Therefore, formalin oil for the surface diffusivity and capillary process is not the best, but for the other processes, for the other properties, it has actually been very nice. So overall, we can say that among all the liquids for the tribological testing, formalin oil was the better lubricant or best lubricant. Now, we are going to conduct tribological tests wherein, if you guys need a break, let me know. If not, I can still continue. I don't have any problem to continue.
Yeah, you can continue, Professor.
Okay, thank you.
Or if you want some water or something, you can take, and then you can.
Oh, thank you. So yes, so the first thing right now, so far we have been working on sample preparation, right? That's all okay. Now we wanted to see what happens when we change the normal load in the tribological testing. So I said that why do we want to say, okay, I'm going to test with one load for 3 hours, and later on I'm going to test it with again 3 more hours, another load? Why do you want to spend too much time? And let's do a particular specialized test called step load test. Okay, so wherein we can continue to change the load in the one test itself. So for 15 minutes, we can apply, for example, 10 Newton. Later on, we can apply 20 Newton, 30 Newton, all the way. You can keep on increasing. So that sort of test is primarily we are going to see. But then there may be a question about, in the beginning of the sample, in the beginning of the experiment, there will be something called running in stage. What if this running in stage is not taken into account? And that's why to explain that, first test was done by increasing the normal load from 10 to 100 Newton. And then the second test was done on a sister specimen. So for example, you can take a 90% aluminum oxide, fill the pores with the oil. 2 samples you can take, same samples, sister specimens. One specimen is like when you are increasing the load. In the another sample, you are basically decreasing the load. That means you start with 100 Newton, later on you go with 90 Newton, etc. So if you superimpose the friction coefficient curves, they are quite nicely matching except for the first few 15 minutes or so. So in principle, one could do a pre-alignment of the samples by like 30 minutes or 15 minutes or half an hour, that's like, pre-alignment. Then if you will conduct your step load experiments, it's perfectly all right. Okay, so that's what we have been always doing the step load experiments to see that here I'm going to first of all show that if you have a fully dense alumina specimen, but in the dry condition, there is no lubricant at all, then the friction coefficient is changing from 0.3 and almost goes to a steady friction coefficient of around 0.18 or 0.2 sort of. But now if you add a lubricant on the top of the surface, then the friction coefficient can decrease, certainly. So formalin oil is definitely a good lubricant, and it has certainly reduced the friction coefficient just for the lubricated situation. Remember that we wanted to compare our infused samples with the lubricated samples also. Okay, so in the lubricated stage itself, it was able to decrease the friction coefficient. Now let's continue, and then we can basically do for all the substrates. That means I'm going to have 70%. Excuse me. Okay, yeah, I'm going to have for 70%, 80%, 90, 95, in fact, 99.5% dense sample. Seems like I didn't put the latest graph. Anyways, and then you have also a sapphire single crystal sample. Okay, well, some of the first 3 cases, obviously it is an infused case, and the last 2 cases it is actually a coated situation or a lubricated situation. So this is all the friction coefficient data. Now to make it easier for you, we can plot it this manner. So I'm going to say that I'm again taking right now it is as a function of the sliding time, but I'm just saying that excuse me. Yeah, I'm going to say that I wanted to understand which is a better density for the substrate. So therefore, I said I'm going to plot my friction coefficient as a function of density of alumina, that is 70, 80, 90, etc. and for different loads. Okay, whatever 3 loads we have plotted, you can nicely see that there is sort of a like a dip at 90%. That means my 90% alumina density seems to be actually an optimal density to yield the lowest friction coefficient. So let's see why that is the case. Just give me a second, please. If we look at the, so the reasons are the following. So as we are changing from 70% density to 99.5% density, what is happening? Definitely there is a grain growth after 90%, but from 70% already the porosity is actually is in this way, it's decreasing. And then these are the factors, right? So for example, in the case of 90% dense sample, your amount of open porosity is quite high, so that will help the lubricant to replenish on the dry surfaces. But also you need high hardness, right? If it is a very, very soft material, then what can happen, like especially in the 70% sample, lot of grain fracture will happen, especially at the grain boundaries. We have thoroughly studied it. I'm based on the study only I am talking about. So the grains are going to fracture, and that is going to lead to some debris. That means you are going to end up as third body abrasion. So that means you are going to have higher friction and higher wear rates. However, in the case of 90% dense sample, relatively much more necking is present between the grains as compared to your 70% dense specimens. So this combination of optimal hardness, still able to have some sort of porosity to bring the oil. So that is actually the reason why 90% seems to be a better density as compared to 70, 80 or 95. See, 95 or 99% density, they have much higher hardness as compared to 90% samples, but they don't have any open porosity to bring your liquid. Okay. Okay, now that we have characterized the friction coefficients, definitely we can also get rid of this. Yeah, now that we have finished characterizing the friction coefficient, we can also characterize the wear coefficients. So wear coefficients are, one is the so-called dimensionless wear coefficient, another one is the dimensional wear coefficient. So if you look at the Arcard's wear equation, so you have Q equal to, where Q is nothing but actually your wear rate, which is given in millimeter cube, that is amount of volume of the material that is removed per meter of the sliding distance, and therefore it is nothing but K is your dimensionless wear coefficient that is plotted actually here, and F is the applied normal load, and H is the hardness of the softer material. So one could plot both the dimensionless as well as dimensional wear coefficient, and we can see that if you especially look at this wear coefficient, you can see that for the higher dense specimens, the wear coefficients are very small, almost like 10 power of -8. In the last 2-3 cases or so, I could not detect any mass changes at all. So that means these are very this is wrong. It's not 90%. It is greater than 90%, guys. Let me correct this one here. So these are very low wearing systems. But in the case of 70 to 90%, that is these 3 cases, it's a medium wearing system. Of course, the 90% seems to be having again a small value around 10 power of -7 millimeter cube per Newton per meter. So not only friction coefficient, but in terms of wear coefficients also, it is doing fairly well. Okay. Yeah, so then we have looked at the wear mechanisms for all the samples investigated in detail, both the counter bodies as well as bottom sample, and in fact also wear debris, and have found out that all the samples are actually undergoing abrasive wear mechanism, and they are failing, or not actually failing, but the wear is actually occurring through these 2 modes, which is transgranular plus intergranular fracture modes. However, for the 70, 80 and 90% dense specimens, it is predominantly intergranular fracture, that is the fracture is through the grain boundaries, because these are the weakest points. However, for the 95 and 99.5% dense specimens, these are all the SCM pictures, but I'm just giving you a final conclusion, right? So for the 95 and 99.5% dense specimens, typically the debris were having much smaller sizes as compared to the initial grain sizes. So that can actually explain that the grains have fractured, so the crack has propagated through the grain. That is, it is predominantly transgranular fracture for the highly dense specimens. So during this, not only this crack propagations has happened, but many places there is a tribosintering phenomena that has happened also. Okay. So one could actually measure the roughness before and after the wear to see that, especially for the highly dense specimens, the roughness has increased dramatically because there is a breaking of the grains. However, for the other specimens, already remember that these specimens have got roughness because of this debris compacted areas and some porous regions are there. So already they do have roughness. And now due to the wear, the roughness did not significantly increase because there was also this oil. So that has actually tried to decrease the this debris quantity on the surface. Okay, now previously we were looking at the friction coefficient at room temperature. Then what if we will now take a container of oil in the tribological testing equipment, and this container of oil, for example, is heated to high temperature. So I have heated that to almost around 150 degrees Celsius or so, and then the viscosity from initial viscosity, it has dropped down to a very small value of 10 centistone. So even with such a change in the viscosity, you can see that the friction coefficient is only changing by 0.05 only. Okay, so for a low viscosity, that is which is 10 centistoke at room temperature, sorry, that is at high temperature, and this is 150 centistoke at room temperature. So At room temperature, higher viscosity, obviously should have lower friction coefficient. Again, refer back to your Stryback curve, right? So the viscosity is playing a role, but not very significant. Then we also have conducted tests where we change the sliding speed. So in the case of reciprocating sliding, speed is nothing but 2 times your stroke into frequency. So we can play with the frequency and say that I'm going to change my frequency from 1 hertz to all the way to 24 hertz. That is what you see actually as these steps. So this step means it's at 1 frequency. You have to read the right hand side, and then later on 6 hertz, then it's 12, 18 and 24. Again, not just keeping load constant, but I have also changed the load. So again, you can see that the friction coefficient is decreasing, but not too much. It only dropped by around 0.06 or so. So speed and viscosity do have an influence, but it's a very small influence for this system. Okay. In the previous case, remember that your counter body was never infused or was never coated. Only the bottom specimen was lubricated or was impregnated. But what if even the counter body would also be coated with the oil or would also be lubricated with the oil? Okay, since we already have seen that 90% sample, the 90% density was more or less the optimal density, I started saying that I will use this configuration and test for 90%. And then the friction coefficient was sort of reaching around 0.17 or so. But very interestingly, if you take the 95% dense specimen, then the friction coefficient of as small as 0.025 is achieved. So in fact, we have given these results to a Swiss watch company, and they found it very interesting. So they were looking at that point of time how to employ that in their industry. So remember, your fully dense alumina sample was having very high value. If I can recall, don't recall actually, let me check. Yes, your fully dense alumina sample was having around 0.2, but now with the lubricated situation, we are able to have 0.025. So almost, 1 order of magnitude smaller friction coefficient was achieved in the case of this, both the samples being coated. Okay. Okay, so the last part, which is something which I personally like, is that we know that this is our Stryback curve, right? Stryback curve is basically plotting your friction coefficient with your Hertz number. Hertz number is this particular thing, viscosity into speed by load, that is your normal load. So you have several regions, that means your boundary lubrication, mixed, hydrodynamic, and for this ball and flat, you have also elastic hydrodynamic. So obviously you would like your friction coefficient to be as small as possible for most of your applications. So it's important to generate your Stryback curve. We know that if you are creating textures on a surface, then we know that our Stryback curve actually shifts downwards as well as they shift leftwards. Okay, so if your surface is simply a flat surface with the oil, then that is your black curve. But if you create some sort of micro dimples on the surface, then your friction coefficient value can even further be reduced. That is the concept we wanted to use and say, how can I now first create dimples on the surface? Yes, there are several micro machining methodologies like laser machining, electron beam machining, etc., electron beam lithography, etc., FIB electron beam lithography. But if I want to employ it on ceramics, 2 problems are there. First of all, you need relatively big areas of pattern surfaces. It's not that 5 by 5 micron or 100 by 100 micron is going to be sufficient. Your stroke itself is 4 mm. That means my counter body is going to move 4 mm totally in this direction. So your 4 mm, and then this is actually thickness is going to be diameter of your counter body. So it's actually a macroscopic area we need to texture. So how can I texture? We can use laser, But then the problem is the the surface chemistry of your material is going to change when you use laser, and also the material that was ablated out of your sample, that will redeposit on the sample again, thereby creating quite a lot of undesirable topologies, which is not very good. So laser patterning is not the best. So then I said, okay, let's then go ahead and find out a nice methodology. How can I pattern the ceramics? That's what is the next part about. Okay, so the next part of patterning is actually, it's called colloidal lithography. So for the case of ceramics, people have already employed colloidal lithography in the past before I have used this. But then what is the novelty that I have done during the PhD? Let me explain that. Before I wanted to explain you the novelty, I will first of all explain you the brief process. So you have something called master template. That master template can simply be a leaf also, because leaves and flowers, they also have got patterns. Or it could be from clean room facilities. You can go and pick up a micro patterned surface, or you can also buy. Nowadays people are even selling these templates with micro features. Once you have this template, you can pour your PDMS. PDMS is polydimethyl siloxane. It is again nothing but like your phone cover, that is silicone material. So you can pour it on this and let it dry, and after, it's actually called curing process. Okay, there is a covalent bond formation that happens, and after the curing, and once you demold the PDMS, you're going to end up having the negative impression of your template on this PDMS. Now I'm going to pour my slurry. Remember, we have made our alumina slurry, deagglomerated slurry. That slurry is what I'm going to pour on the PDMS, and again carefully dry it. If you are not very careful here, you are not going to get your results. In fact, first time I have done it, I was able to get it. Again, later on, I was not able to get the reproducibility. So that's when I had to do a thorough scientific in-depth understanding of the drying process. Okay, I'm going to talk about that scientific part of the drying. So once you dry it nicely, you're able to basically obtain textured ceramics which are having similar topographies as your master template. If you are starting with some sort of pillars, then you're going to end up having pillars on your ceramic. But if you're starting with a dimple, then you're going to have dimples on the ceramic. Okay, so that's what the master template. What I have taken is a laser ablated polycarbonate that we got from a spin-off company from EMPA in Switzerland. So this is quite huge. Of course, for my applications, I have just taken sufficient areas. Okay, now on that, this is how the PDMS replicas look like in the literature. Until my work, always people have used very thick PDMS, like around 1.5, 2 or 3 mm thickness. But in my study, I came up and said, not just like that, there was a scientific reasoning. I came up and said, okay, let's go for a thinner PDMS, because this is going to help in the better drying process of your ceramics. Okay, now this is the so-called in situ slip casting, or you could also call it as colloidal lithography. Now this PDMS, which is textured, remember this particular region here is actually textured, and this is not textured. Similarly here, this is not textured, while the middle part is actually textured. So on this textured region, if you simply pour a very little amount of alumina slurry, then you are more or less going to make it like a coating. But for our tribological test, we need bulk specimens. So if you want to make bulk specimens, in the slip casting, the same assembly that we had, between the filter paper and this silicone mold, I'm going to place my Silgard, this thin Silgard, I'm going to put it here. Okay, so that I can able to pour quite a lot of slurry into these molds, and finally able to achieve very big green compacts, wherein this interface, the slurry and the PDMS interface, that is actually where my texturing is going to happen. Okay, I said that the drying was very important to understand, right? So initially, when you had poured your slurry. This is actually your slurry of water plus polyacrylic acid, and this white dots are actually your aluminum oxide nanoparticles. This slurry, when you have poured on your PDMS, which is, for example, containing these sort of textures, it could also be dimples type. And this is more for a schematic diagram. To begin with, the time t equal to 0, this is very nicely suspended. However, as you are letting it dry, how you're drying, simply because this liquid is evaporating from the top, as well as your PDMS, it is having intrinsic porosity. That means this water, yeah, if there is any audience who understands the wetting part, PDMS is a hydrophobic material, which means if I put a liquid water on it, the liquid water is not going to spread on it. Okay. However, the water vapor can actually pass through PDMS. That is it's an interesting scientific discovery, or let's say, yeah, scientific discovery I came across, or actually I made during this understanding. So the liquid water will not pass through, but water vapor will pass through. So the drying is actually happening in this direction. Some part by evaporation and some part by permeation of water vapor through PDMs. Okay. Now, also, apart from this removal of water, there is definitely some sedimentation happening. One could actually model it by Stokes' law, and there is also some Brownian motion, but our particles are not that small, so we can neglect the Brownian motion. So typically, we can see some sedimentation happening. And after a while, I have even observed experimentally that there is a clear water that is present on the top. Just like, you take some muddy water, pour it in some beaker and wait for a while. On the top, you will be able to see clear water, right? So it's the same thing I have seen. And then finally, I'm able to see something like on the top surface, it just felt like, oh, it has completely dried. Now, at this point, because I did not know that there was a liquid, I have actually tried to demold and found out that inside there is still quite some liquid because it is still evaporating. Okay. So this is an intermediate stage, and you have to therefore leave sufficient amount of time so that all the liquid firstly comes up through capillarity process and then undergoes evaporation. Here it's direct evaporation and permeation. Here permeation is continuing, but evaporation, it has to first undergo a capillary process. Then finally what you get is a green body after you demold this material from this PDMS. These all phases are experimentally observed. So for this drying process, which contains all these transport phenomena, there is a lot of mass transport is happening, right? So we can actually develop a model. So I have developed a model. It's an analytical model. It's linear because the mass transport is happening in this vertical direction. So therefore, it is one-dimensional linear drying model. That's what I had developed. So what can happen is that if you look at here, first of all, there is the liquid is having capillary transport in this direction. Then there is an evaporation, which is given by the rate of evaporation is R2. Capillary transport has got rate is R1. And then the liquid is not entering, but vapor is entering. So water vapor permeation is given by R3. And then filter paper and your plaster of Paris. These are very, very, what do you call, these are very porous and like very quickly absorbs water. So R4 is not the rate determining step. So essentially, we need to look at R1, R2, and R3. Now look at these couple of things. One is the height of the slurry, that is how much you're pouring, and then W here is the thickness of my PDMS. Remember, in the literature, everybody was using W equal to 1.5 to 3 mm, etc. But in my case, I was saying that let's go ahead and use smaller film thicknesses, smaller PDMS thicknesses. Okay, so for the case of R1, the capillary transport, one can model using Darcy's law, and evaporation, one can model using Carrier's correlation equation. This is not a very precise equation because it's more an empirical equation that people have come up with. So therefore, I have also, to verify it, I have also experimentally measured the evaporation rates of the slurries for like a prolonged period of time by using a high precision weighing balance. And I have corrected that equation by using some factor between the experimental values and theoretical values. Then for this water vapor permeation, one could use Fick's first law. By using this, we know that how much amount of liquid is present here. Okay. If I know the volume, and if I know the rates are nothing but volume per time. So one could actually say that my drying time for the whole slurry, that all the liquid has to be removed, is actually coming up with this complicated equation. But don't worry, I'm going to show you what is the thing. So the first thing you have to see is my drying time is directly proportional to the slurry height. That is the first observation. Then the second thing is it is inversely proportional to the PDMS thickness. And the third thing is in all my rate equations, there is something called base area. So that means, am I pouring my slurry on 1 millimeter square area or 10 millimeter square area? What is that area on which I'm pouring? Because, for example, in the kitchen, if you want to, for example, cool down your hot milk before you feed to your baby, all right, it's normally we take a very big area and we try to, cool it down easily, right? So that was your base cross-sectional area. So all these three terms are actually containing base cross-sectional area, but your drying time is independent of this base cross-sectional area. So if I pour it on 1 millimeter square or 100 millimeter square or 1 kilometer square area, the drying time will be the same. So using these three conclusions from the theoretical model, now we needed to test experimentally. So the theory is saying that in the first graph, let us focus on the first graph here, which says my total drying time, it is plotted as a PDMS thickness W. So this the black curve is actually the theoretical one, and these blue points are the experimental points, which is very nicely fitting the theoretical observation. Then second plot is drying time as a function of slurry height. Again, here also experiments and theory are nicely matching. Then the third point is it is independent of the cross-sectional base area, right? So I have here done for 3 points. And you see that it is also again fitting the theory. There are some implications from this. Okay, what are the implications? In the literature, maximum thicknesses of the ceramic samples that were micro textured are only okay, this is the one I'm talking about. Sorry guys. Yeah. So here, because let me restart. For the PDMS, we were always saying that literature people were using 1.5 to 3 mm of thickness. Okay, so because of that high thickness, if I am pouring little amount of ceramic, it was taking quite a lot of time. And if I am pouring more amount of volume of slurry, because the water vapor permeation through PDMS was pretty very, very slow if you have a very, very high thickness. Therefore, people were never reporting or never able to prepare bulk samples of ceramic. But because we understood the scientific part of the drying, we are now able to prepare thick specimens like bulk specimens, no longer simply tapes. People were making only thickness of 200 micron maximum, while in my study, I was able to make thicknesses of 10 mm. We can also further continue, but I was able to make it until 10 mm. That is the first implication. Then the second thing is people were able to pattern surface areas of maximum 100 mm square. But with this approach, because it is independent of the base area, I had patterned for 12,000 mm square, which is way much higher than what literature has made. So that means upscaling is actually possible. Lot of surfaces can be patterned by this methodology. And we had given the KT, we did the knowledge transfer to a Swiss watch company. So what are the patterns that we were able to prepare? Are nice dimples, okay, with different geometrical parameters. What are the geometrical parameters? Here it has the so-called diameter, and distance between the pillars is called pitch, and depth of the cavity, not pillar, I'm sorry, it's a cavity. Yeah, distance between cavities, that is pitch, diameter of the cavity as well as depth of the cavity. And here you can see that they are hexagonally arranged. In principle, I can say that I want them to be arranged in a square fashion, right? We can do that. Okay, or we can also say in a honeycomb manner we wanted it to arrange. So different things are possible. And we can also change the area fraction of these cavities. All these are geometrical things, and so you can actually change all of it and fill these now with lubricant and study the tribological properties. Not only this sort of dimples, but this is actually like a tear shape, like a triangular sort of shape. So even such topographies I have made, and then these sort of ridges we can make. In principle, if you will zoom in any region, you will see that there are also mesopores as well as these ridges. Not that the sample is fully dense. And recently, in the SRB project, my postdoc, they were also looking at another templating methodology, and they are able to make these sort of things, wherein it's a micro cavity, and if you will sinter them carefully, then you can also have some small mesopores also. So that's right now the samples are ready, and we are about to test the tribological properties of these patterned surfaces. Okay, so before I would like to conclude, I want to show you something interesting. Zirconium oxide, as I said, it's a dental implant material, right? So I had a thought saying that, yeah, definitely my teeth are in contact, upper teeth and the bottom teeth. So tribology is important. But what if the food that I'm eating, like ketchup or some other foods, right? Water, etc. If they don't go and get stuck onto this implant material, perhaps it will reduce the amount of microorganisms that grow on my teeth. That was the thought I had. So I'm going to show you some interesting video without too much of explanation. If you have simply zirconium oxide, a dry zirconium oxide, let's see how the water drop would behave. Both ketchup and water, you see, in the dry case, they are spreading. But when you coat it with something, then the drop and ketchup both are just sliding off. So they are not getting stuck onto your zirconium. So these are some of the recent curious observations my research members in the group have made. So I thought I'll show this before I conclude the talk. All right, so we can conclude essentially that the friction coefficient of the alumina composites infused material, because 90% density was better, right? So infused samples show better friction coefficient or lesser friction coefficient than the lubricated samples, and as small as 0.025 are obtained. Then wear resistance is pretty good. You have low wearing systems, you have medium wearing systems, and one can actually control depending on the application. Then we have tested, but I have not shown in this presentation, but certainly formalin oil was the best lubricant. And then we also know that the density wise, 90% density was the better. And micro texturing is possible now on aluminum oxide, zirconium oxide. It can be extendable to some other ceramic systems also. And we have come up with a nice analytical model, which is also explaining, experimental observations are there, which is validating the theoretical model that I have developed. So future scope is, after we have made these nice samples, we are going to test the tribological properties, also test with bacteria to understand and prepare maybe anti-fouling surfaces and things like that. So these are some of the relevant publications that came from those works, and some more are in pipeline. So I would definitely like to thank once again Professor Ravi Shankar for giving this opportunity, and all the funding agencies and collaborators and team members for this interesting projects. And thank you all. Thanks to all the audience for listening at this time of the day.
Yeah, thank you, Professor. And so now audience presenter, those people who might have got the good amount of knowledge. So now the floor is open for you to ask your questions if you have anything. Thank you. So audience, you can raise one after other. You can raise hand or you can ask some questions. Okay, thank you. My request is that you please introduce so that the speaker can know who are you, so that you can ask the question.
May I, sir?
Yeah, please go ahead.
Very good evening, everybody. Thank you, Professor Ravi Shankar and Kumar sir, and to providing such an opportunity to meet Professor Haidar from IIT Gandhinagar. And myself, this is Dr. B. N. Naidu, working as assistant professor in Centurion University, Orissa. Ma'am. And it's really nice talk. I have gone through entire your work. And I have two means one question, and I have got two suggestions from you also. Actually, your observation on liquid water and vapor interaction with PDMS material really helpful for me, ma'am. Where I'm using PDMS material for my research for organ on a chip, and that is really good insightful thing. And second thing, I have found one research topic like research area like a coating of teeth for implanted teeth to avoid microbes. So that's really nice one. Maybe I will look into this kind of research area. Thank you so much for that. And I have one means it's not a question, but I want to know the word in situ, ma'am, where we can use this kind of a word. I have seen this word in different research papers. Just I want to know that.
Okay. Thank you so much for your very nice encouraging feedback. Definitely, first thing before I explain the in situ word, I am open for collaborations and of course, we cannot do everything. Great, nice teamwork will be able to help us in achieving to bigger heights. So then let me talk about in situ. Right, in situ essentially means that if you're talking about, let's say, characterization tool, so if there is an SEM, and for example, if you're able to do a tensile testing inside the SEM, then it's like an in situ testing because you're able to do the test as well as look at the samples as the test is going on. So in this context, the word in situ was used because I am able to use colloidal solution. Normally for casting, I would use colloidal solution. That's the slip casting. But
Okay.
during the slip casting process itself, I'm able to texture my surfaces using these PDMS templates. That's why I
Okay.
called it as in situ slip casting.
Okay. Okay, one process along with another process, simultaneous, you can say that, tandem.
Yes. Yes.
Okay. Thank you, ma'am. Thank you so much.
Most welcome. Any other questions, audience? Okay. If there are no questions, it means either you fully understood or you didn't understand.
Yeah, utilize opportunities. Okay.
There was a comment by B.
Some people and
Don't be shy. Just okay. There are some more questions. One more question. What are the composite materials used for tribological applications in industry? That depends, Rajkumar. So, what industry are we talking about? Are we talking about medical? Are we talking about marine? Are we talking about food? What industry? No, it depends. So it's very difficult to say answer for that. Then initial surface affect the coefficient of friction. Can you speak out, Mullah, instead of the, if that is the right name, I hope. Mr. Mullah, could you kindly speak to me directly?
Mullah, can you ask, madam? Hello.
Hello.
Yeah, go ahead.
Yes. Madam, my voice is audible.
Yes, yes,
Yeah,
I
yeah,
can
you are
hear.
audible now. Go ahead.
Madam, if you make the 2-3 samples, so every samples if has different surface roughness, then that initial surface roughness affect the COF or not?
So as you have seen, all the samples, the surface roughness is reducing as we have increased the density, isn't it?
Yes, madam.
Okay, but remember, we are never testing a dry specimen. We are always coating or infusing the high viscosity liquid in it. And that oil is flooding your surface roughness. My coating,
ma'am.
the
So-
oil is not having a thickness in the range of 5 nanometer, right? It is way much higher than the roughness.
Okay, so the direct contact is not come into the picture.
It may, because we are increasing the load, and if you remember our
Yeah.
strike curve, right?
Yes, yes. Yes,
Yeah,
if we
so-
increase the maximum load 200 Newton, 300 Newton, then the direct contact come into.
Yes, we may be very much in the yes, in fact, we might be in the boundary or the mixed lubrication regime when we are talking about our porous specimens. But that will still have some type of a oil between, even if it is couple of monolayers, because the oil really likes alumina. The interfacial van der Waals force of attraction we calculated, that is suggesting that the oil likes to wet on alumina, right? So that means there will be few monolayers separating out. It may not be exactly solid contact, but the oil thickness will be very, very less. It will be squeezed out for higher loads.
Okay. Okay, thank you, madam.
There are questions in the chat. I'm requesting you to please ask them. Okay, let me read. Why are you so shy? Did you guys not have dinner today? No energy to ask me?
Mhm. So madam should have lost the energy, not the audience actually. You should take the opportunity to ask her.
Okay, I have the following queries. Somebody called Tadi Shiva.
Hello, ma'am.
Yes,
Yeah,
yes,
Shiva, go ahead.
Actually, some problem at my end, ma'am. Internet issue is there. That's why it's
Okay,
in chat box.
Yeah,
Okay.
go ahead.
Let-
Shiva Prasad, go ahead.
Yes, ma'am. So, ma'am, while we are preparing slurry, you said you end up with some agglomeration of particles, right, ma'am? How you overcome this agglomeration?
Okay, so if you buy nano powders, the dry powders are going to have quite a lot of agglomeration. So now you have to break those agglomerates, right? But even if you break them, it's possible that these will come together in the liquid state also. If you remember that slide, first of all, you took the dry powders. We have added some liquid, which is polyacrylic acid plus water, and then we adjusted the pH. Why did we adjust the pH? So that these particles, after we have mechanically broken them, they will not come again in start agglomerating. We don't want that. So we are essentially trying to say that I'm going to give each of these particles some charge so that they will be in stable equilibrium. Okay. So now for the mechanical braking, what did we do? One is the probe sonication. Simply, it's like a probe. It will essentially give some energy and break down the particles. And it is not sufficient. So we had also done some low energy milling. Just like you have ball milling, which is a very high energy milling process. Now in a slurry, you can add some alumina beads, which are around 1 millimeter or so, like very big beads. Then you can nicely close the container and put it on these rolls, which will run for 2 days or 3 days. So that will help to reduce all the agglomerates. And finally, if you will do, if you will check with the laser, the particle sizes, you are going to get a single distribution curve, but not the double distribution. If you get a bimodal curve, it means that the agglomerates are still present. If you get a single distribution curve in the particle size analysis, then it means that most of the particles are nicer deagglomerated. Does that answer your question, Shivprasad?
Yes, ma'am. Yes, ma'am. And what is the basis for selecting surface active agents, ma'am? If they can reduce the agglomeration by any chance, what is the basis?
We look at the zeta potential, right? So we are going to, once after we, first of all, you are going to add some of these surfactants. When you add a surfactant by some volume, then we are essentially also dispersants, both of them. You're going to look at zeta potential. Zeta potential is the surface charge on your particles in the slurry. So small, highly negative zeta potential means it is a stable solution.
And ma'am, how can we scale this agglomeration? Is there any scientific basis?
Sorry, how can you?
How can we scale this particle distribution or agglomeration within the matrix?
How can you scale it? What do you mean by scale?
Scale, I mean to say, for example, if we added some percentage of particles.
Particles or dispersants?
I mean, if you can take alumina powders, and later stages, if we end up with the agglomeration, how can we scale? How can we scale this agglomeration?
I don't get still the word scaling. Do you want to get rid of the agglomeration or not?
No. So for example, he may be asking like, for example, if you are mixing the polymer along with some ceramic particles, like Al2O3, you are mixing with aluminum matrix or something, for example. So he want to know whether it is uniformly distributed or percentage of agglomeration. Am I right?
Yes, sir. Yes, sir. Percentage of agglomeration.
Percentage of agglomeration. So
Yes, sir. Yes.
how do you scale?
How do we measure? How do we measure it?
Okay, so are you saying that is my polymer dispersed very well in the solution? Is that the
Yeah,
question?
so yeah, well dispersed.
How particles are well dispersed within this polymer matrix?
No, there is no polymer matrix at all. It is
My
actually
query
ceramic
is-
particles. Yes, please ask the question once again.
If we mix some particles like metal nanoparticles in a polymer matrix, there are high chances that these particles, metal particles, can agglomerate. By any chance we reduce this agglomeration, how can we prove that agglomeration is reduced?
As I said, right?
She has already told that that sonication
Later.
and other things can be used for reduction of the agglomeration. Now you mean to say that you have still agglomeration is there? If it is there,
Yes.
then how do you quantify?
Yes,
You want to quantify? Whether,
Yes,
for
ma'am.
example,
To scale means I mean to say quantify.
You mean to say that 10% agglomeration and 90% distribution, or 80% distribution, 20% agglomeration? You want to say like that?
Yes, ma'am. Yes, sir. Yes, sir.
How do you quantify like that?
Okay.
How do we quantify?
Yeah, I got it. So when you will, for the quantification, what you can do is, you can simply take a fully agglomerated slurry, which means you're not going to do any of these steps at all. You'll simply pour your powder into your solution and look at the solution with the DLS, dynamic light scattering experiment. Okay, then you're already going to get a bimodal distribution of the particles. Why? Because your particles, smaller particles is going to show up as one single peak, and your bigger agglomerates are going to show up as second peak at the right side in your x-axis. So two peaks are going to come. Okay, based on this, you can already say that, okay, how much is my agglomerates present initially to start with. Later on, once you do your mechanical processing, that is, you're trying to break your agglomerate at a different stage. After 5 minutes of breaking, again do the same DLS and see that your second peak is actually going to diminish. After 20 minutes of de-agglomeration, the second peak is again further going to reduce. Based on this data, you can actually quantify how much is your agglomeration present in the material, in the slurry.
With the help of DLS curves.
So she told, can you name the process again? That is what he was asking.
No, I think he got it. It's by using dynamic light scattering.
Dynamic light scattering curves. Yes,
Okay.
yes, madam.
Dynamics light scattering. You
Yes,
just
yes.
otherwise, no. For example, if you are having some component very small or something, then you can also go with micro CT and other things. I don't know whether you can do it or not, but sometimes micro CT also can give normally porous and other things. For example, they want to check whether the porosity is there. Same Sriharitha, they use micro CT for using of this, whatever he says, agglomeration and other things.
I would say no, because I mean, yes and no, but if I have to choose, I would not. So the reason is the following. So first of all, if you want to use microcity, if I'm correct, it should be for your sinter specimens. Okay. So all the way you have to complete all your drying steps, pre-sintering steps, and then sintering. Then you will be able to use your microcity. Second thing is even more important reason is that when you're already sintering your specimen, there are some small particles and then there are very big agglomerates. So both of them are going to start sintering. So if your micro CT is certainly going to say in the bulk material, where are all the porous regions, it will tell us. But how will it say how much is the agglomerate? Because right now will not be any agglomerate, no. All the agglomerates and smaller grains, everything is going to start forming solid boundaries in your sintered specimen. Was that clear? In the slurry stage only, it is much more easier for us to figure out, yes, I have an agglomerate. At some point, there is only single grain. But once you have removed all the solution, now all the solid particles are sedimenting and it's like a full powder bed. That powder bed, which is now simply having air between them, you're going to do a sintering process where now the air is actually to some extent it will be removed and solid contacts are going to happen. Powder bed means already solid contacts are there, right? So how can I say that, okay, there was actually here an agglomerate? Because inside an agglomerate, remember that there will still be porosity, right?
Yes, madam.
Okay. Any other question?
So if you don't have question, I think no, many people, you know how this color SEMs comes. Many of the participants may be thinking of normally your institute will have a SEM that will give you ash color images.
Yes, sir. Yes, sir. Black and white. Yes, yes. Correct.
Black and white. So why are you not asking that? See, okay, you see
You
the
thought,
first one.
did you think we were painting it?
No,
So madam is putting some doll and enjoying, okay, and flowers. So you can ask such questions. No, normally many people will ask us this type of questions, and many people will have query that how these colorful SEM images are coming. So I think Professor Harita, you can tell them how this comes.
Sure. So these are simple SEM pictures. In fact, these things here on the right side are what our students has won in the India's competition last year. And these images are all from our group. This first three are from my own work in postdoc, and these are from my students. So these are simple SEM pictures, and they're all finalists for the nano artography contest by Drexel University. This year, these are all the finalist images. So if you actually see the background of this image, it was pretty much like a sort of a grayscale, right? So we can color the SEM pictures in some softwares. Some open softwares are there, like GIMP. Some people use Photoshop. Some people simply use PPT. And then you can simply color it. And then that's how you got it. This is like, the middle picture is nothing but your banana leaf SEM picture. Okay. And this one is actually your lotus leaf, right? So, and this is some other leaf. This is actually the cement. So very, if you're very passionate, if you actually are interested too much, then you will start seeing all things like, I see many times things are dancing, some things are sleeping, like, these particles, like here you see an elephant, several things you will start seeing in the micro and nano world. It's very fascinating. So, thanks for asking that question.
Okay. People understood how to do?
Thank you. Yes, sir. Thank you
There
so
are some
much. sir.
softwares we can color them by using those softwares.
Yes, you named it GIM, GIM, ma'am.
GIMP.
Professor Haritha, you can put in the chat box
Chat box, it is better.
so
Yes,
that
ma'am.
they can understand.
Yeah, sure. GIMP is one thing, and then so people use Photoshop, but Photoshop is not open. It is a licensed software. So, but then you simply do a Google, you will get more softwares coloring the images. That's the keyword. Yeah, I have already written it in the chat box. So, yeah, that's it. If there are any more questions, I can take it. If
Ma'am,
not,
it is not reflecting as of now.
I've already written.
My message is there.
Okay.
Yes, sir. Your message is there, sir. Kindly write the software. Now it came, ma'am. Yes, it
Yeah,
is.
yeah.
The previous one went to that one particular person.
Okay,
Sure.
yes, it's to everyone.
So you can play with those using these softwares to make good images. Okay. So that no, your acceptance ratio of your papers also will increase. Okay. But I don't know whether the papers will accept these type of things.
No, this is not for articles. This is more for if you like both art and science, then you can try to do this. It's just your own interest. And of course, there are some competitions, so you can submit to those competitions.
So thank you, Professor Sriharitha, for your valuable time, and thank you, participants. Hope you might have had a nice time in understanding the science of tribology and other things. Okay. So thank you.
Thank you so much, and have a very good night.
Yeah. So thank you. Thank you. Thank you, participants. We are ending the meeting. And Uday, are you there? Uday? Okay. So Venkat, cross-check with Uday. Okay.
Okay, sir.
Yeah, because we are ending the session and we have to give the video to the ACT. So make sure that this will be recorded or something. Yeah. Thank you.
Okay, sir.
So, Professor Ravi, sorry to interrupt you.
Yeah.
Is this video going to be posted somewhere on
No,
social
no.
media?
We are not posting anywhere. We are submitting to ACT. It's a CD we have to submit to them. That's all. We are not posting anywhere. If at all we want to post or anything, we will take appropriate permission from you.
Okay, perfect.
Normally we don't do that. Okay. If, for example, the participants, my throat is slightly infected. That's why just now I got this last 1 hour back only. Last 2-3 hours back I just played and came from the ground directly. So I have a lot of shouting and other things happened. So my throat is okay. So what I mean to say is that participants we have to give hard copy to the participants. So some of the slides which are not which are givable to you, you can send to us in a PDF format. Thus, printout we will give you. We will give them. We don't give them the soft copy. We are providing the hard copy because as a protocol for them, as ACT, we will give. But subjected to what are the slides that you will give.
Sure,
so if there are any confidential things, don't give. Definitely, we also don't want those things. So what are the slides that you can give? You can give to us so that we are going to make on this weekend the bounded one, and we will be providing them on the next week when they come physically. Okay. So Venkat Krishna, you can coordinate during this with Professor Haritha. Anyhow, I will put you in CC whenever I write to her so that you can coordinate. Venkat, fine?
Yes. Okay, sir.
Thank you, Sriharitha, and thank you all the participants.
Thank you so much, Ravi, and see you all. Good night.
Yes,
Bye-bye.
hope to see you sometime
Sure,
in
sure.
Tirupati. Yeah.
Yeah, likewise here. See
Thank
you.
you.